Hi, 10:30. We are starting 11B today. So what you see up here is perspective and symmetry. And we actually are going to take out the perspective part. I noticed that as I was going through the homework problems, the perspective's been taken out. So we're just going to deal with the symmetry. I fixed the notes, but you probably printed them off already. So just disregard the part about perspective in the beginning of your notes. You'll have to skip over a little bit. But we're going to start with and end with symmetry for 11B. So there are many connections between mathematics and visual arts, as we know. People who do painting and sculpture and architecture use a lot of the mathematical concepts in their art. It's kind of amazing to look at them and see that. There are three of the deepest connections found in these particular aspects of the visual arts are perspective, symmetry, and proportion. And with those things, we've already talked about proportion a little bit, but we're going to talk about it a little bit more in respect to the golden ratio and the proportion of 1.618, which is a really cool proportion that's used a lot. And then symmetry, of course. Now, we'll explore how Renaissance mathematicians and artists discover techniques for painting and the idea of symmetry with their paintings. So it'll be kind of cool. And I love this, the cross-curriculum part of this section, looking at that as we're going through mathematics and the use of symmetry. So symmetry refers to a kind of balance or a repetition of patterns. So when you see symmetry, the pattern that you notice, I don't know if you want to look over here, the pattern, it goes up and then it goes down on the A, it goes down, across, and down. What happens with symmetry is it's a property of an object that remains unchanged under certain operations. So when you see this little blue line, that means if I reflected the object, it would be unchanged if I just reflected it. I don't know how to explain this. You can see my hand. It just goes 180 degrees. You're going to see that it ends up looking exactly the same, which is what we mean by unchanged. H, you can reflect it horizontally with the H. You can just reflect it 180 degrees that way, or you can reflect it upside down as well. And rotation is something else. So rotation of an object, you can see here with the O and the S. And it has something to do not with folding, but with actually just taking this point of rotation and rotating this object about that point. And then if we go 180 degrees, you're going to notice that it looks exactly the same. All right, 360 degrees rotations don't count. They don't count because obviously if you rotate something around a point 360 degrees, it's going to end up in the majority of cases, well, if not all, I just don't dare say always, but it'll end up being itself. But if you can do other degrees like 120 or 180, where you rotate it and it ends up being exactly the same as before you rotated, then that is a rotational symmetry. So it remains unchanged when rotated through some angle about a point. So with the S, you can state that 180 degrees, if we move this point around till it ends up right there, your S is going to look exactly the same as it did before. All right, there's also a translation symmetry. A pattern remains the same when shifted to the right or to the left. Translation means slide. So if you slid a certain amount of units to the right, this pattern is going to be the same, as long as you get this part of the X right to there. You slide it to there, you slide it to there. That's translation symmetry. So those are the three types of symmetries we're going to be talking about or learning about and discussing. Identify the types of symmetry in the star. Now this is a type of homework problem. What we're looking for is how many times can we rotate, or how many times what places can we reflect this star about, and it would remain unchanged. For that, I'm going to look at this on our homework here. Identify the types of symmetry in the star. So reflection symmetries. So that means if I always think about folding it along this line right here, and if I take this side and fold it over there or reflect it, it ends up being exactly the same on that point. So that would be one reflection symmetry. Now, if I take and rotate it this way, that would you can either fold it or you can think of it being totally flipped around to this line right here, reflected around this line, they call it. That's a second reflection symmetry. And in fact, that's going to be the same with every single one of these points. This would be a third. So I can reflect this whole star about this line of reflection that I've labeled number 3, and it will look exactly the same. And I have 1, 2, 3, 4, 5 points, and that's exactly how many reflection symmetries there'll be. I can do one right along here and right along here. So this would be 4, and this would be 5. All right, so that would be 5 reflection symmetries. And then the rotational symmetries, that means how many times can I rotate? And after the rotation has occurred, the star looks exactly the same, then that's how many rotational symmetries it has. Now, I think of these as points. So if I'm going to make a little dot there to make them stand out better. If I take this point and rotate it however many degrees it is to right there, that's star after being rotated, and I'm rotating it about this point in the center here. So I rotated about the point in the center so that this point ends up being right there, then that's going to be a rotational symmetry that will occur, and the star will still be the same or be left unchanged after that rotational symmetry. So that's 1. I can move it to here, and it's after rotating to there, it's going to be exactly the same star. So that's 2. And then it can be moved to right there, which is 3, and then it can be moved to right there, which is 4. So there are 4 rotational symmetries that can occur to where the star remains unchanged after all 4 of those. So we have 5 reflection symmetries. We can fold it or we can reflect it about 5 different lines. We counted them, and then we rotated 4 symmetries. Now, it's interesting. When you're dealing with stars or 5-pointed stars or 10-pointed stars or 3-pointed stars, every single time, I was going to try to do a 3-pointed star. I can't draw. But there are 3 points to that star. You're going to notice that every time, if these were drawn the same way, I'd have to have a computer to do that, all these points, you would have 3 reflections. So you would reflect through this line, and through this line. So that would be 1, 2, and 3. 3 reflection symmetries, and then you rotate once and then twice, 2 rotational symmetries. Note that the third rotation would be a 360-degree rotation, which wouldn't work. That's how we deal with symmetries. Now, the other thing that I wanted to point out is what is the angle? You're going to have to figure out the angle of rotation. And how we do that is we know that all the way around this star, so 360 degrees around our total degrees. Now, when I go here to here to here to here to here, that's 5 different points, right? If I go to here and all the way around 5 times, I'm going to be back at 360. So each one is 1/5 of 360 degrees. So if I take 300 on the star, 360, and divide by 5, because there are 5 rotations to get back to the 360, then that's a 72 degree. How about I do that on my calculator? 360 divided 72. Helps if I'm on a blank screen. 360 divided 5, is indeed 72 degrees. So that means to this rotation would be 72 degrees. To this rotation would be 72 plus 72, which is 144 degrees. And then another 72 to here is what? 6. Excuse me, calculator. 144 plus 72 is 216 degrees. And then if I add another 72 degrees, I'll get my last rotation that counts, 288 degrees. So my rotational symmetries would be in degrees: 72, 144. What did we say next? To there, and then 216, and then 288. Those would be my rotational symmetries and angles. And there are a few problems you'll have to figure that out, but that's how you do it. It's not too bad. Note that there's generally one less rotational symmetry than reflectional symmetries, because the last rotation is the 360 degree rotation that doesn't count. But anyway, that's how you do those. Now, you're going to get a few little questions on your homework with that, and also draw an equilateral triangle and how many degrees can the triangle be rotated about its center so that it remains unchanged in appearance. So an equilateral triangle means that all three sides are the same and all three angles are the same. And there are 3 points. So there would be 3 of the reflection symmetries, but it's asking in specifically what the rotational degrees are. So you would take your 3 points that you would rotate and divide that into 360, and you get 120 degrees. So that would be 120. That would be another 120 to make 240. And then the 361 is last. So there would be those 2 rotational symmetry, 2 rotations that the equilateral triangle would go about, and it would be 120 to 240. All right, next one is draw a square. How many degrees can the square be rotated about its center so that it remains unchanged in appearance? So here we have, if we move to here, that's 1, and then 2, then 3, and then the 4th one would be back to 360. So we have 4 points, basically. We're going to divide 360 by 4 first, and that's 90. And each of those rotations then will cover 90 degrees. So we start here, we go 90, and then another 90 would be 180, and then another 90 would be 270. So 90, 180, and 270 are the 3 rotations that, or the degrees that the square can be rotated about its center and remain unchanged. The last question is a regular pentagon. How many degrees can the regular pentagon be rotated about its center so that it remains unchanged in appearance? And this is already drawn. Again, it has five points. So that's what we would divide 360 by. So 360 divided by 5 to get each individual rotation in degrees will be 72 degrees. So that means if we start here, we can pick either of the 5 points to do that. We would have a 72 degree rotation, and then another 72 would be 144, and then another 72 would be 216, and then another 72 would be 288 degrees. Not too rough. All right, I kind of showed you how to do that on the star, but that's what you'll be doing. Hope you understand that. And then moving on to tessellations, which I call tessellations. The book, the homework calls them tilings. And the pictures on my PowerPoint are pretty cool in the symmetry, the tiling and tessellations. You can see them better here. So the tiling is an arrangement of polygons that interlock perfectly without overlapping. They don't overlap and there are no gaps. So you see here, this is a 6-sided polygon. I call them hexagons and triangles. And together they form a great tiling. There are no overlaps and no gaps, which are pretty important. All of these are in the same boat. You just see different types of shapes. And they're all beautiful, I think. You see them a lot with floors when you see a tile floor and whatnot. But anyway, they call them tessellations or tilings in this book. Now, sometimes you can see this figure and move it over, and you can continue moving them. This is a flipped or reflected quadrilateral, just like the blue one. The white one is the exact same thing, only reflected, and they fill in the gaps perfectly. And if all the gaps are filled in and there are no overlappings, and it's a great tiling, you're going to have to pick those out in some homework. So just wanted to make sure you understand no gaps, no overlaps. And then this is a reflection from this. So reflection means you see it in this orientation, and then they reflected it over this side of the rectangle, of the triangle, and it shows another tiling. All right, so that's a tiling, and even though you don't have the line going through here because of the white ones, they still are there. And that's it. We're going to start into the next lesson on the next slide, but I'll post this one and hope you have fun with this one. This is a great lesson. All right.